Last time we were looking at products of transpositions, and in looking at products of transpositions, we ended with two questions. The first one was, can every permutation be written as a product of two cycles? And the second question was, since the decomposition of a particular permutation into two cycles is not unique, is there anything that can be said that's consistent about any representation of a particular permutation as a product of two cycles? In this particular video, we're going to concentrate on the first question. So the first question is can any cycle be written as a product of two cycles? So we're going to start by simply looking at cycles. Now, E itself is a one cycle, and E can certainly be written as a product of two cycles, because if I look at 1, 2 composed with itself, that's going to be E. If I compute this 1 goes to 1 and 2 goes to 2. And clearly, if I have any two cycle, I goes to J, it's not very hard to think about this as a product with one term or one factor in it. But if I don't like that, I can also think about I, j as being I, j composed with 1, 2 composed with 1, 2. Because here, if we look at this particular product, what we're going to wind up getting is 1 goes to 1, 2 goes to 2, and I goes to j. And that is simply I goes to j because those one cycles, these are one cycles, they don't count. So certainly two cycles can be written as a product of two cycles. So now let's actually look at an example and think about three cycles. So let's see. What about 1, 2, 3? Now, we've actually seen how to write 1, 2, 3 in the previous video as a product of two cycles. And one way of doing it is to let 1 go to 2, and then we're going to compose that with 1 goes to 3. And if we do this computation just to make sure that I haven't done something silly and something stupid, we can see that this indeed has 1 goes to 2, and 2 stays put, so 1 goes to 2. And for 2, 2 goes to 1, and then 1 goes to 3, and as a consequence, 2 goes to 3. And finally, there are no 3's here, and 3 goes to 1, so consequently, we close the cycle. And so obviously that works. So now the question becomes, what about, well, we can generalize first of all to any three cycle. If I have A, B, C, I can take this exact same pattern. A is playing the role of 1, B is playing the role of 2, and C is playing the role of 3. So if I look at the permutation, AB followed by AC, and we compute that, it doesn't take a whole lot to realize that what we're getting is A goes to B, and B stays put, so A goes to B. And then we have B goes to A, and then A goes to C, so as a consequence, B goes to C. And then finally, we have B goes to A. No, rather, we're on C's rather. There are no C's there, and C goes to A. So we wind up having C goes to A. So this is obviously a way to write ABC as a product of two cycles. Well, let's see. Can we go up to 4 cycles? So 1, 2, 3, 4. let's see if I can do that. Now, I want to kind of generalize what we've done, and there are a couple of ways of looking at the pattern. The way that we were starting is that the first permutation in the composition, which of course is the rightmost permutation, was the, let's kind of remind ourselves that 1 goes to 2 goes to 3 had 1 goes to 3 and then 1 went to 2. That was what our, if we back up, that was what we wound up having right here. 1 goes to 2 and 1 goes to 3. Let's see, did I copy that right? Nope, I got that wrong. So let's get that erased and get it copied right. Going again back, what I want to do is I want to remember this particular thing. So 1 goes to 2 is on the right permutation. So 1 go. Gotta remember to move my pen. So 1 goes to 2 is that permutation, and then 1 goes to 3 is over here. So I want to kind of generalize that idea on my 4 cycles. So let's see. I need to erase that guy. And we'll now say 1 goes to 2. Now, we have to now, if I'm thinking about it, so I've got 1 goes to 2, but 2 goes back to 1. So I'm going to let 1 go to, let's think, maybe it's 3. And then maybe 1 goes to 4. So that is one idea. So now we're going to check this idea. So we start computing, and of course we're computing in the right to left way, and we want to of course start off with 1, and 1 goes to 2, and 2 stays put, so 1 does indeed go to 2. Now 2 goes to 1, and 1 goes to 3, and then 3 stays put. So yeah, 2 goes to 3. Well, what about 3? There are no 3's there. 3 goes to 1, and 1 goes to 4. So we have 3 goes to 4. And then it turns out that when you look at 4, 4 goes to 1 is the only place where that appears. And so that works. Now, the idea is, can we do this for an in cycle? So let's just take the easiest in cycle. Let's look at 1, 2, 3, all the way up to n. Well, our pattern seems to be 1 goes to n, and then 1 goes to, not 1 goes to n, 1 goes to 2. One goes to 2, and then 1 goes to 3, and then 1 goes to 4, and we keep going all the way until we get 1 goes to n. Now, it's important to realize that in the middle of this thing, every term looks like 1 goes to a k, and the k is running from k equal 2 on this end up to k equals n on that end. So let's now try and compute this particular product. So we start off with 1. And 1 goes to 2, and there are no 2's. So as a consequence, 1 goes to 2. Now, what about 2? Well, 2 goes to 1, and 1 goes to 3. So 2 is going to 3, and there are no 3's over there. So as a consequence, 1 goes to 2 and 2 goes to 3. Well, we continue and we start to think about what happens to 3. So we realize that there are no 3s. There's my first 3. 3 goes to 1, and 1 goes to 4. And in this part, there are no 4s. In this, no 4s. And so we have, that goes to 4. And now it repeats. When we are looking at what happens to 4, 4 goes to 1, and from here, the next one is 1 goes to 5. So 4 goes to 5, and then there are no 5s in the rest of that. So we're going to wind up having 4 goes to 5. And in general, what's going to happen is when we get to k, we're going to have this term here. And what we'll have is no k's before then. The next term will be 1 comma k plus 1. So k will go to 1, and 1 will go to k plus 1, and then there are no k plus 1s past that, and so consequently, k goes to k plus 1, and this continues all the way up until you get to n, and it's easy to see that there are no n's until you get here, and n goes to 1 at that point, which completes the cycle. So we now have every n cycle can be written in a particular product of cycles. So what I want to do is actually get that clean. 1, 2, 3, all the way up to n can be written as 1 goes to 2, followed by 1 goes to 3, followed by 1 goes to 4, all the way up to where you finally get to 1 goes to n. And again, we can do this with a general n cycle by simply replacing 1, 2, 3, 4, 5, and so forth with A1 goes to A2, all the way up to AN. And then in pattern matching, all of the 1s become A1s, all of the 2s become A2s, and so on. And so we get this particular decomposition. It's not unique. And one of the things that I want to challenge you to do is find a second different decomposition for a standard n cycle. You can start with just 1 through n into a product of 2 cycles. We will talk about that in the next synchronous online meeting of the class.